Hi, my name is Sheldon Logan from the VLSI Design Automation Lab in UCSC Santa Cruz, that is the University of California, Santa Cruz. I will be talking about our robust power grid synthesis methods. Power supply network synthesis consists of generating a power grid to meet the various power requirements of a circuit. These requirements are electromigration, such that all the wires have a specific lifetime. The voltage drop at all the nodes in the circuit are within a specific threshold, and the voltage droop, the transient voltage drop, is also above a certain threshold. The voltage thresholds are required to ensure that the circuit can meet its timing constraints. Lower voltages lead to slower circuits, which can violate timing. Modern circuits have large power constraints, which exacerbates the power grid synthesis problem for two reasons. One, large power and power densities among integrated circuits means higher temperatures, which makes it harder to meet the electromigration constraints. Also, large temperatures increase resistivity of wires, which also makes it hard to meet the voltage constraints. An example static IR drop map for the IBM PG3 benchmark is shown here. As you can see, the voltages are within the design constraints. The equivalent temperature map for the IBM PG3 benchmark is shown here. As you can see, in certain areas of the IC there are large temperatures, which will exaggerate the electromigration constraints and make it hard to meet the voltage constraints. A transient simulation of the IBM PG2 transient benchmark is shown here. Initially, all the voltages are 1.8 volts, which is the supply voltage, and then as the circuit warms up, the node voltages approach their steady state value. Notice that different portions of the power grid switch at different times. The supply voltage in the benchmark is 1.8 volts, and all the node voltages stay within 10% of that value, which is 1.6 volts. One important question in power grid synthesis is how robust is the power pin placement? That is, if one pin fails, will the power grid still be able to meet the requirements, both from an electromigration standpoint and a voltage standpoint? This figure shows the static IR drop violations that can be caused by a single power pin failing. The failing power pin is shown with a star. Here is a transient simulation for the same benchmark, IBM PG2 transient benchmark, however with one pin failing. The black circle represents the location where there are node violations due to the failing pin. The goal of single pin redundancy is to ensure that the power grid can still meet its constraints, even if there is a failure of any single pin. First, we find which pins need to be redundant, and then we find potential pin locations that can fulfill that redundancy. We formulate this problem as an integer linear problem and solve it using GLPK.